Hello, I'm Sayed. In this video, I present a novel proof of why the speed of light is constant. Surprisingly, you will see that this strange phenomenon is nothing but a visual illusion, and therefore it cannot have any real consequences. In modern physics, the speed of light is postulated to be the same for all observers, regardless of their motion relative to the source of light. This is very confusing and counterintuitive. How is this possible? If we think of light as a particle, we cannot understand or explain why the speed of light is invariant. However, here I show that if we think of light as a wave, this mystery is solved easily. This circle represents a spherical wave. The radius of the wave increases over time. The color fades to show that the intensity of the wave decreases as the radius increases. The wave attenuates as it propagates because its energy is spread over a larger surface. This dot represents a particle. No change happens during its motion. There is no attenuation. A particle does not change as it moves, but a wave does. An important property of a spherical wave is its curvature. The curvature is the degree to which a curve deviates from being a straight line, or a surface deviates from being a plane. Let us compare the curvatures of these two circles. The smaller circle has a bigger curvature, and the bigger circle has a smaller curvature. Mathematically, the curvature is defined as the inverse of the radius. If we have the curvature of a spherical wave at a given point, we know the location of its center and the length of its radius. That is, we know the point where the wave has started its motion and the distance that the wave has traveled. None of this information is known for a moving particle. Consider an object like an airplane moving along a straight line. All parts of the airplane move at the same speed in the same direction. The velocity vectors for all points on the airplane are the same. We can treat the airplane as a particle and use a single velocity vector to describe its motion. This is not the case for a wave. Each point on a spherical wave has a different velocity vector. This is true not only for a wave of light emitted from an isotropic source, but even for a very narrow beam of light emitted from a highly directive source like a laser pointer. Note that the velocity vectors of the points on the wavefront have different directions. Unlike a particle, we cannot reduce the wavefront to a single point and assign a single velocity vector to it. Now we come to the main part of our argument. Consider a spherical wave of light in vacuum expanding at a constant speed of c around its center. We choose 2 points A and B close together on the wavefront. As we explained, these 2 points have different velocity vectors in different directions. The vectors are normal to the wavefront. That is, they are at right angle to the surface of the wave, the same as the radii of the sphere. Note again that if we have the curvature, we have the radius and the center. Let an observer move towards the center of the wave at a speed of v. We know that when we are moving towards an object, it seems that the object is moving towards us. So these two situations are equivalent. The velocity vector of the observer can be added to the velocity vector of the wave in the opposite direction. The resultant velocity vectors are shown in green, and they correspond to an illusory wavefront having a different curvature. Again, the new velocity vectors are normal to the new wavefront. This is the key point. The apparent curvature observed by the moving observer is different from the real curvature. A different curvature means a different radius and a different center. It is especially important to note that when the observer moves towards the center of the wave, the apparent center moves away from the observer. But what is the speed at which the apparent center moves away? To answer this question, note that these two triangles are similar. The distance OA is proportional to the length of the vector C, and the distance OO' is proportional to the length of the vector V. So while the real wave travels from the origin O to the point A at the speed of C, the apparent center displaces from O to O' at the speed of V. For illustrative purposes, we have shown the angle between the two rays OA and OB very large. In practice, these two rays reaching the eye of the observer are almost parallel, and therefore the 2 points A and B almost coincide. As a result, the apparent radius O'A equals Ct plus Vt. That is, the radius increases at the rate of C plus V. Combining these two effects, we conclude that the observed wave travels apparently at a speed of C plus V minus V, which is equal to C, independent of the observer's motion.
This is a spherical wave of light. In free space, its radius increases at the speed of c. For an observer moving in this direction at the speed of v, the radius apparently increases at the speed of c plus v, and the center apparently moves away at the speed of v. As a result, from the observer's point of view, this wavefront appears to have a speed of c plus v minus v. C plus v for the radius and minus v for the center. Now I have good news and bad news for the proponents of the special theory of relativity, a theory based on the postulate that the speed of light is constant. The good news is that the constancy of the speed of light is now clearly proved using geometrical optics, as I presented here. Now we know how it happens. The bad news is that this phenomenon is caused by a visual illusion. It is not real. We cannot expect any real effects from a visual illusion. Conclusions such as time dilation and length contraction based on this visual illusion are false and lead to contradictions, as I explain in the next videos.